So
Stop sharing.
at this point, I would like to ask all the speakers, please, to turn on your video and unmute yourselves. Good, I see almost everybody. Good, I see everybody. We have 10 or 15 minutes left, or as long as anybody wants to stay, I guess, but 10 or 15 minutes left to ask questions and have general discussion. So I am watching the chat, so if anybody has something that they want raised, you're welcome to put it into the chat. But also, let me just now invite anyone in the audience, if you would like to ask a question, please do. Please turn your video on, unmute yourself, and ask your question. And I will not call in particular orders. I see a couple of people in the chat. Go ahead.
Did Jeremy answer Richard Letton's question about associative algebra? That's the only one I see. Maybe there has been some that went private.
Yeah, yeah. Jeremy, did you see Rich Letton's question about associative algebra here? But
yes,
it's really about
yes, so,
it's really about persistent databases, I think, more than associative algebra. But
well, so I guess the thing I would say is, first off, pretty much in any database, your table mathematically is already an associative array, whether you think of it that way or not. That's what it is. If you look at what, pretty much any relational database or NewSQL or tuple store or whatever, the tables essentially have the mathematical properties of an associative array algebra. And so therefore, you can do matrix-like operations on it. And whether you choose to implement those directly as matrix-like operations or just do some math and then say, okay, and then go implement those using whatever the native constructs are, those are perfectly reasonable ways to do that. And I would say that, for instance, one database we work with is Apache Accumulo, which often uses a large sparse matrix representation. And we built an add-on library called Graphulo, and coincidentally, Accumulo and Graphulo both fully support, this matrix view of working on that data. So I'd say it's pretty straightforward to bring these ideas into databases.
It really seems to me like a game changer that databases and sparse matrix operations, people have understood that they're connected forever. But I think it's only with the really efficient, fine-grained hypersparse implementations that that Aiden pioneered and that Tim has brought to fruition that you really have the possibility that now database the labels on the rows and columns can be anything, because you can hash them to 50 or 60 bits and just pretend that they're matrices. That brings up a question. Yeah, go ahead, Jeremy.
So I would agree. I mean, we've implemented associative arrays just using indirect strings, and of course that's incredibly flexible and nice when the stuff isn't super large, but it becomes prohibitive, and Tim's and others hypersparse stuff allow you to essentially play the game that you described, and now it makes it very, very practical. It's not only can you just work on an almost arbitrary large key space, as we call it, but you will also get this really high performance at the same time. And we've started using that in our own work, and it's proved, have some papers coming out exploiting that. I've written a number of papers at exploiting that. We had one that we published in Grapple that exploited that fact. So it's really great stuff.
I see a question in the chat from Zach, and I think this is probably for Richard. It's, could you elaborate on what you meant on the slide where you wrote you eliminated the symbolic phase using a randomized algorithm? I think that's about randomized incomplete Cholesky, but I'm not positive. If I've got the wrong reference, Zach, correct me in the chat. And Richard, I can't hear you. I'm sorry. Are you? Oh, you took off your microphone.
Yeah. So I pinned Zach, and this is for Aiden, actually.
Oh, okay. Sorry, Aiden.
Yeah. This is what do you mean when you wrote eliminated in the symbolic phase using a randomized algorithm?
I don't think it's me.
Zach, are you here?
How many times I have talked about randomized algorithms today?
Well, Zach.
Oh yeah. Okay, that's me. That's to me. Okay. Hi, Zach. Thanks for your question. Well, so the way the algorithm worked was there was a phase and HIP-MCL. First, you need to figure out how much memory you need. Otherwise, you can't tell how many phases you need to do. Remember, there was a period where you have to decide how many columns of the output you can form, because if you try to form all of them at once, you're going to run out of memory. And in the past, what we used to do is we ran this so-called symbolic phase, which is doing the sparse matrix multiply, but not generating the output. So it would keep track of exactly what would require, and it's almost effectively doubled the runtime. Maybe not, but 80% up. So instead, we integrated a randomized algorithm, which has actually been known for quite a while, but I don't think it has been implemented on a distributed memory setting at all, and much less in any setting, as far as I know. So it actually worked very well. It's simply, John knows this, it's by Edith Cohen. I'm happy to send you the reference of, you can also find the link in our paper to the original algorithm. It kind of predicts how many non-zeros each column would generate without doing the full computation.
Okay. So I had muted everybody during the talk, and it is now possible for people to unmute themselves. But I see a couple questions in chat. Let me repeat a couple. Muhammad Osama, actually this is for Aiden again, so I'm going to go to a question for somebody else. Alex Pothen asks, could you elaborate a bit on the randomized incomplete Cholesky algorithm? And I think Alex is talking about Rasmus King's thesis and what's happened since then.
Yeah, I can say a couple of things about that. Incomplete Cholesky, the general idea of incomplete Cholesky is that we generate non-zeros. But if the non-zeros are so close to zeros, we might as well get rid of them. When you do this to a graph Laplacian, the thing is that graph Laplacian has the nice property that if you do Gaussian elimination, like if you just like eliminate rows and columns simultaneously, what you're always gonna have graph Laplacians to work with. So your intermediate matrices are still graph Laplacians, which means instead of eliminating single non-zeros, you actually get rid of edges. So you actually think completely graph theoretically. And what happens is that because all the intermediate matrices are still graphs, you can just work with graphs. And then you can start looking at what happens when you eliminate. So there's this thing called a Y delta transform from circuit theory, which is that if I eliminate a vertex, what I did is I created a clique on its neighborhood. So there's this it goes all the way back to elimination trees, that type of ideas. But the connection when you deal with graph Laplacians is far more direct, is that you actually just get a set of edges. And then once you have a clique, you have some pretty good ideas of which ones to get rid of. I mean, you just pick a random subset, and then I think it's some schema based on picking by the weight of the new edges. And this creates, on the implementation side, this creates a lot of issues, because now you no longer have very good predictive ability to figure out where your non-zeros are anymore. So there's you don't know where the fill is, and it's kind of generated on the fly. And getting the kind of the randomization to kind of reconcile with the deterministic way to predict memory acts and so on. This is where a lot of the challenges come up in implementing this kind of algorithm.
Yeah, thank you, Richard. I find it just stunning that this decades and decades old preconditioning heuristic that people have used forever actually has provable properties if you use it with randomization in the right way. Let me turn to a couple of questions about sort of building blocks and how you write software for this. And I'm going to start with Muhammad Osama's question for Aydin. Perhaps this is a philosophical question, but Aydin, the question is, would you define compressed sparse row, compressed sparse column, and a mask to be the building blocks to implement general direction optimized graph algorithms using graph plots?
Strong wording. Given the constraints that are in the second part of the question, which is direction optimized graph algorithms, I would say, yeah. I mean, if I were to take on a new project that solely did that, I would start with those indeed. That's not limiting. That's not to say the 100 different sparse matrix formats that's been developed in the last couple of decades. But really, if I were to start a project for graph algorithms, you really want to access random rows and columns. So CSR, CAC are really more important than you would have realized. For things like matrix vector, where the dense vector is in question, you can actually be more creative. And because you don't need to have random access to columns or rows. But I would say that for this use case, I would do it myself that way.
Okay, thank you. We have a few more minutes. Let me encourage people to keep putting questions in the chat. And so still on building blocks, but maybe a little bit lower. Tim, I wanted to ask you, the finite state machines for doing, you know, taking Fred Gustafson, one of the very first developers of fancy data structures for sparse matrices, and updating him to finite state machines encoded in 2 bits of a zombie is pretty mind blowing. But I wanted to ask you again a sort of maybe philosophical or nuts and bolts question, which is the sort of locking, the implementation of these little finite state machines, which are happening in principle on every row and column, but of course not in actuality, is just amazing. And it's a very shared memory, multi-threaded concept. And of course, one of the holy grails of high performance computing is to be able to do that sort of thing in a distributed memory setting. You know, that was the motivation for the design of UPC years ago, and many other things since then. Have you thought about, I know you have thought about distributed memory versions of these algorithms. Do you foresee using similar ideas to the ones you do in shared memory, or do you think that the distributing setting is just completely different?
You mean using this finite state machine in a distributed setting?
Or similar, or something similar, you know, with enough aggregation and so forth, or whatever. Or do you think it's a totally different problem in distributed?
I think, yeah, my guess is it would be a totally different problem. So this is assuming a shared memory atomic. I think for a distributed memory solution, you really need you need a hierarchical matrix. You need a matrix of matrices of matrices, it's matrices all the way down. And I think Aydin has looked at this kind of data structure. This is the kind of thing that you really need for distributed memory computing, I think. And then you get a sparse matrix of sparse matrices, and then you don't have individual finite state machines that get shared across nodes of a machine. I don't think that would work very well. This works really well for a single shared memory atomic, where you can access the memory atomically.
Yeah.
So I might chime in there and And again, I think if you think about this from the hypersparse perspective, it's certainly something we encountered when we implemented associative arrays a decade ago. We had also, of course, had implemented parallel matrix libraries, and we thought a lot about how would we merge those concepts. And what we realized is as we worked more in the associative array and hypersparse world, that we would just have processors working on almost random subsets of edges, right? I mean, doing load balancing partitioning was very tricky. And so we would just let processors say, we're going to give you an approximately, everyone was going to make sure they get, if we can just give them an approximately equal set of edges, that's pretty good. And then we realized, because we're in this hypersparse thing where everyone has the global indices, and remember, parallel matrix libraries are really just local to global index mappings. But if you have, everyone already has the global index, we realized the decomposition operation was just addition. So if you just look at your algorithm and say, imagine decomposing each one of my matrices into a sum of matrices, a sum of hypersparse matrices where maybe each piece owns a little bit, but you don't need to worry about this. And then you just know that, okay, as long as my math works, that I can just kind of add these up together. That actually eliminated the need of doing any of the traditional partitioning schemes that we had to do in the past. And so we never implemented. So, even 10 years later, we still don't have the traditional block cyclic distributed type of associative array, because we're just, okay, just addition. Just at some point, we're going to invoke some addition, and that's our decomposition operation, which I think is very elegant because it switches decomposition from a kind of partitioning computer science thing to a math thing. The decomposition is just, how does this algorithm decompose under the summation of matrices? And I'm not saying it solves all problems, but it's just a different way of thinking about it that I think when you go into these hypersparse distributed cases can help you solve some problems that you wouldn't otherwise be able to solve.
We are at our official closing time of noon. There are a couple questions still in the chat, and I myself am happy to stay on for a little bit longer to answer them. I will give everyone permission to go when they want, but let me first close the official part of the session by asking for a big virtual round of applause for all of our speakers. Virtual rounds of applause are a little bit ineffective in Zoom, but there you go. And thank you all, and thank you everyone who came for coming and participating in the session. I hope you've enjoyed it as much as I have. A special shout out to Jeremy, my co-organizer of the session, as well as the leading speaker, and to the SIAM activity group on applied and computational discrete algorithms, which whose auspices it's organized under, and which I encourage you all to join. So thank you, everyone. If any of the speakers would like to stay on for a few minutes, I will keep reading questions.
I actually want to interrupt you and say that we should do the virtual applause to John Gilbert, because he's the only person who has taken the whole effort to organize this thing, emailing, creating the GitHub website, making sure we hold this, and we get exposure to our work, and he's just doing all the work for us. So thank you very much, John.
Thank you, John.
My pleasure. Okay, I'm just going to start reading questions out of the chat now. And Aiden, Richard, Tim, Jeremy, you are released from your duties if you wish. Feel free to say goodbye if you'd like. Let me see, where did I leave off? Glenn Brook writes, it would seem that applying masks at the element level does not map well to vector processing units. Have you given any thought to vectorization? I think that's probably at least for Tim and Aiden, maybe for everybody.
Let me, oh, no, I'm not muted. So the masking, no, you can use the mask with vectorization. The mask, I mean, it becomes, let's see, you get a conditional statement test inside a vectorized loop, for example. But the other thing you can do is you can hoist that mask up to a different level, and the innermost kernel stays vectorized, but the mask tells you which loops you want to do or not. And so, for example, in a dot product, if you're doing a mask dot product, the mask tells you which dot products to do. So if you think of triangle counting, you're doing a pile of dot products, but you don't need to compute them all. You only need to compute the ones for which the mask tells you. So each mask is enabling or disabling an entire dot product, which could be 1,000,000 entries long. So they don't fight with each other.
Well, maybe the question was really someone thinking in terms of these as more like dense matrix operations, which vectorization really matters. I guess the two answers is vectorization doesn't really matter all that much here. We don't actually need it because it's mostly bandwidth to DRAM limited computations we're dealing with. But if they mattered, it would still be doable with vectorization simply because almost all x86 AVX instructions actually accept the mask these days. You'll see that you can decide which things to turn on and off. Now, I don't know about the GPU land, about how their operations accept the mask. But at the moment, it's not a problem anyway, because as Tim said, we're mostly dealing with, look at all the things that you need to compute, do the dot product for those elements. So there's not much of a need for vectorization yet.
Okay. I'm going to read a question for Tim, which is fairly detailed, but I think that's all right now. It's this is Kazem Chesmi asks, "Hi Tim, what is the difference between zombie entries and those invalid entries in Chalmod up-down? I mean the entries that are removed after initial factorization." Okay, so Chalmod,
Yes.
as some people on the call know, is a well, I'll let Tim say what the question means.
Okay, gosh, it's been so long since I've written an update downdate for trauma. So let me think. So the Chalmod is what it's doing is an update and down. For those of you who don't know what it is, it's doing an update and downdate of a sparse Cholesky factorization. So I factor matrix, and then you have a downdate, and that removes some entries from the factorization. And I handle those a little bit differently. I do edits of each column independently, and that I have gaps between the columns, and so they grow and shrink inside their own little spaces. So I'm not really exploiting the idea of zombies there. The idea of zombie here means I'm moving stuff around again, which is not very parallelizable. The power of a zombie is that I just kill an entry, and none of the entries around it have to move around in the data structure. So all the other threads that are working on the matrix don't see the change at all. It's totally independent. And so that's the difference, I think, between the zombie and the update downdate strategy I use for Chalmod.
Okay, thank you.
If memory serves. It's been so long since I've written Chalmod update.
Sounded very plausible to me.
I think that's what I was doing there, and the zombies are different. Yeah.
Are there other questions? I think I have exhausted the chat. Is there anything that anyone else would like to ask or discuss?
Alex wants to make an announcement.
Oh, yes. Okay, thank you. Okay, thank you. I had missed that in the chat. Alex Pothan, who is the chair of the activity group on ACDA, points out that ACDA is also organizing sessions at the SIAM annual meeting, which is happening virtually starting next week. And in particular, next Monday, July 6th, from 9 to 11 and 2 to 4 Eastern Daylight Time, so 6 a.m. it begins for us here on the East Coast, but also in the afternoon. There are 8 ACDA talks at the virtual SIAM annual meeting, which is a double-header mini-symposium there, which I hope will be as well attended as this one was. I think that will be a lot of fun. Michael Pelletier, I think, asked Alex for the link to that. If anyone has the link to that, put it in the chat. Otherwise, it's easy. It's easy to find by Googling ACDA and this IM annual meeting.
So I would also like to just comment, I mean, my sense is that at a normal SIAM meeting, the attendance of this session would have been around 20 to 25 people. And I think at our peak, we were about, 90 or so people.
That's
so,
right.
And that's typically what people have been seeing in this virtual world, that you get a sort of 3x increase in your community. And I think that's just fantastic. And it really just allows us to really make this available to a much broader audience. There's so many people have so many good reasons why travel was difficult for them in the past, whether it be physical or family or other reasons, that this really just does and create a much more accessible experience. As much as I do miss getting together with you and all, I think the ability to get the material out to a broadest audience without any discriminatory aspects of it is really wonderful. And so I want to appreciate SIAM and John and everyone for organizing this and helping us, reach just a bigger and hopefully better audience. So thank you very much.
Yeah, thank you, Jeremy. I think, as we go on here, everyone, SIAM included, is learning how to do this better and better. And it's very clear that, stretching out into the future when finally the COVID crisis is over, technical meetings will certainly be different forever, even though I don't think we know exactly how at this point.
And just to build on that, I would say that, the news has not as been good on the COVID-19 front as we had hoped. And so we expect this mode of operation to continue for quite a while yet. And I would challenge people that this is an opportunity to really perfect online capability, whatever it is. Like this next several months, putting your time into perfecting this and making it as good as possible, this moment won't come again. And so if we can leave when we do get back to some better state with respect to COVID-19, if we have mastered this ability, that'll be a something that we can point to, that we really have as a long-term benefit, is that we will have mastered this. So I encourage people to really explore, try different things, and learn and share. And this has been great, and so I just encourage people to take advantage of this opportunity.
You're here. Okay, I will bring the session to a close now. Thank you again to everyone who was involved, everyone who attended. I look forward to seeing you all virtually again as soon as we possibly can.
Great seeing everybody. Thank you.
Great to see you all.
Thank you. Great seeing you.
Bye-bye.